Okay, let's just have a introduction on discrete math. We should do this before we actually going into all the topics in discrete mathematics. Let me just share a file. So this is the core introduction for it. Yeah. And what is actually discrete mathematics? So discrete mathematics, I'm using two example here, an analog clock and a digital clock. So these two clocks are different in the way, of course, they are showing similar time, but I'm just going to use this to differentiate between continuous mathematics and discrete mathematics. So continuous mathematics deals with continuous function, so differential integral calculus such as those. Yeah. So uh, the numbers within a certain range, they are infinite numbers, real numbers. But when we talk about discrete mathematics, it deals with mathematical topics that analyzes data with separated values. So this is such as integers, so like 1 to 2. So very definite in there. So you can see here in analog clock that the arms, the long and the short, the longer and shorter arms can just move. But when they stop, they can stop anywhere between any integers. But when you look at a digital clock, they are just doing integer numbers there. Yeah, of course, some would argue that, well, what about the resolution? Yeah, of course, when we see the digital clock, the resolution is just until uh, 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 1 second to the power of -1, right? Like that in there. Yeah. So, but when we talk about analog clock, is it has infinite numbers of values within between any range. Yeah. So when we are studying the discrete mathematics, the structures are is that the calculus that some of the students have studied, some of you have studied, the study of things that change continuously. You know, it changed continuously. And for example, how long does it take to walk from here to campus? So, well, we can make an approximation, but it's not really a certain value in a discrete way being presented. But discrete math, the study of things that can be counted easily. When you count some number of students in a class, you cannot say 2.5 students or 2.2 students. They're either 2 or 3. Yeah. Or how many letters are on these slides? You can count it. Okay. And also the math techniques particular to discrete objects is the counting and combinatorics. So you when counting numbers, and then when you see how many combination that I can take 2 people from 5 members in class, or how can I get the number of winners, the first, second, and third winners from 10 contestants that joining the competition. Yeah, like that, countings and combinatorics, also graph representation. This is very much useful in IT, in algorithm, when we want to find some kind of path, path from one point to another. When we do some search, what is the best path to take so that it is efficient and effective? Yeah, and probability, of course, probability is to see the chance of things to happen. And then logic is actually underlie all the mathematical knowledge that is applicable. Yeah, logic is actually everywhere. All right. And the discrete mathematical structure sounds like math course. Well, the names infer that clearly, obviously, mathematics. But actually, in here we are not doing any programming, at least not a lot. Yeah, but we will do a lot of proofs. Yeah, using pencil and paper, or using some programs. Later, I will advise us to do some programming simulation just to see how the theory being applied. So this is the math underlying most of the computer science. Yeah. So computer science, of course, there is a major of computer science. Students are studying mainly computer science, but other engineering subject or other discipline, definitely they are using computers on that. Or some just using it, some actually doing some a little bit more than just using. They are integrating with something else. Sometimes this comes helpful. Yeah, computer scientists rely on this kind of math to what? Design high-speed networks. So in terms of networking in a company, in office, or even in research centers, they have to do a good local area networks, how to connect them, how to have uh, the network topology so that it will create the highest speed possible being provided. Yeah, that actually uh, using the knowledge of discrete mathematics as the foundation. And then design control of system from simple to complex. This is automation. Some other engineerings like mechatronics, electrical engineering, automated manufacturing, like that. They're using all these knowledge configuration, I would say, so that they will get the most effective and most efficient design. And of course, to design interactive games, you have to do logic and then graphical theory, how to actually make it interesting, make it doable. Of course, you don't want to make games that nobody can actually do it. You don't really want to make games that is so easy that everybody can do it even by blinking their eyes. Yeah, design speech recognition programs, speech recognition using neural networks and such artificial intelligence. They are using lots of algorithm or matrix calculation, probably number system, and graph theory also in that, and create web search algorithm. Again, this is using graph theory and then and some more logic in that. Yeah, so this is the structures of discrete mathematics. Of course, we are not going so much into deep of the topics that I just mentioned now, but it will be useful when going into this deeper topic in the future. Yeah. So the course focus for our discrete mathematics is first is language of discrete math. So the language of discrete math comprises of logic and set theory. Set theory, set subsets, and how some members of set belong to what and another belong to another, things like that, and how they can have things in common, and how we can include that or exclude that. Of course, usually we are using this in the searching theory also. Relation and function, how a certain numbers included in certain function and how they relate to another function, so that we can connect them. And those which are not included, then we can ignore and make our search, make our calculation, make our algorithm becoming more efficient. Counting and combinatorics, I mentioned it before about counting numbers, what is the most efficient time, the most maximum cost or the minimum cost that we can do by applying a certain combinations. Graphs and theories, trees, yeah, graphs, theories, and trees, how this branching into another, and the possibility of if we choose one and then branching to another, can it be taking more time, taking more steps, taking more cost? I don't know. So this is the language of that. Yeah. So about language of discrete mathematics, and also tools for proving things. So it is important also to prove things, and we are using direct methods and induction and recursion, proving things in terms of, for example, if n is an odd number, then what about 3 to the power of n? Is it going to be an odd number or combination odd and even number, and whatever it may be? So when we are calculating some things, then we can get rid of unnecessary components of the equation, components of the function, so that we don't need to calculate them all. So it will save time in the cycle time, or in the processing time, I would say, when we are talking about processors in computers. And the next thing is algorithm analysis. Of course, this is running time and efficiency again. Talking about when you're writing a program, you must know what is your the calculation of each of the components of lines of program that you have, the code that you have, so that it will be making creating or contribute to efficiency in your program. So you know that your program, when it is done, it should take what, 1 second, less than 1 milliseconds, and so on, so that when it is doing some kind of just like to crack a code. That's why now we are advised to make our passwords in the public account, in a social media account, in other accounts, even a private account, that we should have it like at least a certain number of digits. And even in the digit, we should put capital or small letters. Also, we have to put some numbers, numerical numbers 1 to 9, and as well as specific symbols. Why? Because when somebody or someone wants to find crack the code, crack the password, then it will take them forever to do it. And now, a long time ago, my password 4 digit, or even 6 digit, even 4 digits, about 15, 20 years ago, was already enough, because the speed of the processors was very slow. But now speed is very high, so people can just try all the combinations. If I just only have six digit, then it could just take them less than 1 day to find it, or probably less than 1 hour to find it these days. So that's why we need to make it longer and containing more types of digits. Yeah. So that's also talking about algorithm, how we can do that so that it doesn't spend so much time in processing. All right, next is logic and sets. Of course, there are some sets, combination of them. I just mentioned about sets containing members of sets according to their common characteristics. Yeah. So we don't make notions that we are already used to some little programmings, of course. So that's why in programming letter you have to include a certain library, whether you are wanting to name your variables as what? Variables as integers, as floating numbers, as whatever it may be. Yeah. So this is also fundamentals to all mathematical disciplines, because it's logic basically. So when you are using that variables, when you enter some number, the calculation, the outcome, also you have to assign the type of that sets. Yeah. So it is useful for digital circuits and hardware designs. Of course, even in electrical engineering, when we use a digital circuits, it is very helpful that we know that what are the components belong to. And then elementary number theory. So we are talking also some old reliable number like real prime numbers and all that. But because of the combination, we can find some surprising facts also when studying discrete mathematics. And this is also very useful in crypto system. Yeah, crypto system. All that. Let me continue. So some proofs also I already mentioned about induction. And then if you want to debug a program, you need beyond to know beyond a doubt that you can prove it is bug free. Yeah. So you need to check it, especially when you are designing a program later in the future. Of course, not in the subject. Yeah. We are talking about the basic, the foundation of that. I mentioned already in the class about system theory, but I already posted the teaching in a video in the YouTube. Then you can check it anytime to check it again about system approach. So that's why we are talking about now the bigger, from the bigger overview, bigger point of view, and then we go down. So what we are talking about now, this is a bigger point of view about debugging a program. We're not doing any program in here, at least not a lot. But later, when you are doing that, you need to make some kind of a proving mechanism, and it should be reliable. Yeah, proof theory has recently also been shown to be useful in discovering bugs in pre-production hardware. Yeah, so of course we want to do that before releasing anything, because after releasing and there are so many loopholes, so many problems, then it's not going to be sellable a lot. Yeah, and then counting and combinatorics, go into detail on that. Compute your odds of winning lottery, you can use that. This is talking about chance, a probability in a way. Yeah, and important for predicting how long certain computer program will take to finish. Yeah, so when we do that, we can calculate this program. About 20 years ago, I did try to actually create my own neural network programming using MATLAB, and then I create a matrix calculation. It takes I started the simulation, and then to just check whether the error propagation goes to zero, it took me like 8 or to 10 hours. I slept in the laboratory for that. But it was my fault also. I knew it was going to take long, but I rather just hoping that it will take shorter and shorter. But it should depend on my algorithm. Yeah. So, but if we know the combination, the counting methods, and then the possibility, probability, how long for it to take, then probably we just leave it run and then go back after a certain time and then find it to be finished. Yeah, so it is also a good way to do it by doing counting combinatorics, but not on this course. This is, I'm saying, just the overview of what uh, it will be contributing to. And then of course it's useful in designing algorithm and so on. Yeah, graph theory. Yeah, many clever data structures nowadays. We are into so much of data analysis, data science, because data is very important. Data is power. Some people say information is power. So data structures for organizing information is very important. You know what components of the data contributes to and or assigned to. So making programs highly efficient are based on graph theory. So there are some components of that information that contribute to something. It's very useful in describing problems in databases. Yeah. Some students, especially in IT, information technology, are going to be dwelling a lot in database, operating system, networks. Yeah, networks, of course. Yeah, every computer science related discipline will use this. Yeah, like mechatronic, MP, and IT. So, okay, let me just give you a few examples, several examples. For example, this is just a very ordinary example. For example, green or orange. I want to assign your class to a class project type. For example, you are a mechatronics students and you are IT students. So mechatronics students, the project type will be, let's say, I would say it is green, because it involves a lot with automation. It involves a lot with PLC. It involves a lot with motors and all that. So orange, more or less, type is going to be some simulation, programming, and all that. So I'm just making a black box here. I want to describe. So the input is your class. When you mention, for example, you mention your class is empty, and you can see the output is green color. So everybody knows it. Yeah, this is a simple like a sensing. What is the input? And then there are some lookup table. If it is empty, then it refers to green. And then when I put IT, it refers to orange, like that. As simple as that. So this is like a logic things, matchmaking. Yeah. And another, well, it's good job. You can find it out. You can figure out your class project type. But can we make it both are computers? And what about if I make it to be more complex? Yeah. So only one black box there, but can I have it like 200 of them? So I can have so many inputs, and either because so many inputs are coming, or maybe because there are so many calculations in each black box. So we need to have representation of classes and colors and all combination. And this discrete mathematics will help you and me to actually assign that easily. Maybe we can assign similar color for different type because of their similarity. Yeah, they have something in common. Yeah, and you need to describe the class project type. What are the types? Yeah, so that's actually about lookup table making. People say that there is artificial intelligence knowledge, which is fuzzy logic. Fuzzy logic is talking about very much, very, or light, or no, or yes, things like that. Some people get mix it up for a lookup table. Lookup table is like when you go to A, this is the output. When you get to A plus, this is the output. You get to A minus, this is the output, and so on and so on. But they're actually different, but we're not discussing that. But it is also about assigning, assigning what are the outputs if your input is such and such, and what if my function weren't so meaningful? Need a way to list and process all possible description. That's why we need to list all possible description. Later, that's when we are talking about be help in the discrete mathematics, in the future. And let's look at another example, a dark bridge. This is needing some logic, needing some graph knowledge and calculation. Suppose AB, Bill, Kara, and Dana, ABCD, all of them need to cross a narrow bridge, a narrow bridge, a bridge which is narrow, that holds no more than two people. Only two people can go past. So when two people have passed to the other side, then another or two other person can go onto the bridge. So it takes them 10 minutes for AB to cross because probably she's slow. 5 minutes for Bill, 2 minutes for Kara, and 1 minute for Dana. Dana probably the sprinter, very good, to cross respectively. And then they need a flashlight is necessary in order to cross. So two people cross with the flashlight, one return carrying it. So because they only have one flashlight, they have to go, two of them, and then one person have to go back. So you need to count how far, how long they all can get over to the other side of the bridge. Of course, the condition here, the rate on the bridge is the rate on the slower person. Of course, when two person, let's say Dana and Kara, need to cross, Dana takes 1 minute, Kara needs 2 minutes. So both of them needs to take 2 minutes because they only use one flashlight. So the question is this: hurricane is going to come in 18 minutes. So how would they make a program or a plan so that they will be able to miss the hurricane, which is getting over to the next side of the bridge, to the other side of the bridge, within 18 minutes, maximum 18 minutes. So how do we solve this out? You can find it your way, but we can do it by, we can, maybe if you calculate by your head on your writing paper, probably quickly you'll find the step of doing it. But what happens if we have like 10 people, or we have 200 people, or 200 combinations? This is like sending data to a certain servers, things like that. So is one way to do it is by using what we call is the graph theory. So from one side to the other. So what happened with AB and then going back and then AB and so on and so on. You can practice it. We don't do it now because this is just introduction. So label all the ages with walking times. With walking times, ages with walking times. 2, 5 here. If I'm putting my laser pointer here, 2, 5, 10, 5. These are the walking times. And then this is the age where AB will arrive there, or if AC will arrive here, or AD will arrive here, and then comes back again. What comes back here? Things like that. So you can just make it. And what else? So we can find the shorter path algorithm. Yeah, this is used in searching theory also. So of course, this is a simple because there are only 4 nodes. Yeah, 4 nodes, and then of course a limited number of edges also there. But what happens if we apply this to a bigger network? Yeah, so this is also later can be used for bigger searching theory. What else? Oh, this is production line. Maybe this apply to engineering like mechatronics a lot. So if you see station here, this is just a drawing, yeah, but just a simple example. We can calculate with each station here without telling you what other station is, but you can just look at it and says that each station, of course, has its own process time, operating times, and from that station to another station, maybe it takes time to transport. So we can use all the discrete mathematics knowledge to find the most effective steps. Which one? Without wasting more time, yeah, delivering time or processing time. What most time efficient? Which one is more time efficient in terms of time for? Say it looks like this is manufacturing of donuts. How long does the donuts is being made? Yeah, and then collect and produce. And then we can use counting methods can use graph theory and also of course other methods. So these are the introduction of discrete mathematics, and later we will talk more about this uh, in a in the next session. All right, that's it for now. See you later.